Hello everybody and welcome to this presentation. My name is Riccardo Zanon and together with my colleagues Dennis Rademacher we are working for ArcelorMittal in Luxembourg, and together with Professor Gunter Seidl and Professor Damien we have developed a solution which is optimized for highway overpasses with a very critical clearance height, and it will be the subject of this presentation. I will start with the motivation for these works, then showing you the development of the concept, and then the calculation tools which have been used and made available for users to calculate this kind of solution. So, modern highway overpasses are very often integral bridges. Integral because they have the advantage to avoid joints, rod joints, and supports the beams, which are installations which have a life cycle expectation lower than the one of the structure. Very often, this kind of decks are realized by means of steel concrete composite decks. Here you can see an example of the picture, and it's very important that their profile is above the existing clearance height of the way that you have the overpass. Recently, it was developed by SSF Ingenieure a concept, the VFT system, so-called prefabricated composite girder systems, which changed a little bit the conventional composite girder. In fact, instead of having I would say, homogeneous concrete slab, we have two layers. So a first layer, which is a prefabricated deck, which is separate in longitudinal direction, so it's continuous in longitudinal direction, and is already present during the construction stage. And then we have a in situ concrete on top of it. You can see a picture here on the top left. It was used first for standard simple support and continuous girders, where it proved its interest, and it was also used for overpasses. And here you can see an example of a bridge girder, which is fabricated in the workshop, so with a variable inertia. You have a slab which is precast and prefabricated on the construction site, and then the beams is put on the supports by crane. Of course, you have very large hogging moments in correspondence of the abutments, so it is very important to have an important lever arm, so that's why the height of the beam is quite important, and you have a considerable amount of reinforcement for the negative hogging moment. It is a construction type which is very efficient, very beneficial when you construct bridges over existing roadways as well as railways. Here is an example of an impressive long prefabricated composite girder, which is placed by night during the night closure of the railway over the abutment. And the main advantage of this typology is that when the beams are put one beside the other, you offer a platform which can be used by workers directly for finishing the operations of the deck. Here you can see one of the largest frame which was built in Europe with these typologies. It is in Gdansk in Poland, with a span of 65 meters, and as you can see, a quite slender deck in the middle and higher construction height on the side with an important lever arm. The span is 65 meters, is one of very large overpass, because as you can see, you have two roadway lanes on each side. You have a tramway in the middle, and still you have some cyclic and pedestrian roads. So this is, I would say, really an upper limit of an overpass, which is framed without intermediate piers. As you can see, the fact to have a curved bottom flange is very efficient and very also aesthetic. The only negative point is that the clearance height is usually quite constant over the width of the highway. So the critical point, it is not in the middle, but it's rather in a place which is this corner between the dashed line and the curved line. Typical slenderness is about L30, L35 for the midspan, for a span of about 50 meters. Other supports L over 15 and L over 20, and that's why the critical point is about a slenderness at L25, L over 30. Depends, of course, of the kind of clearance height which is imposed. But one of the key concepts of the new development was really to optimize the clearance height, and so to have a straight part in the middle and then to have an inclined part. This permits to have a improved clearance height. In fact, it is possible to, for example, decrease the difference between the road level of about L over 150, L over 200, which for a span of 50 meters correspond to 25-35 centimeters, which can appear as not very much, but it is a considerable advantage for some cases. So let me do a joke. So we felt really that our efforts were to jump over the dashed line as smooth as possible. So we took inspiration from this very famous sportman. We investigated several options. The first option is current in buildings, which is obtaining a haunch by cutting a road section into two and welding it below the road section. This is not really aesthetic. It's of course economical for finishing, but it's not optimized for static, neither for fatigue. So it can be an interest for industrial hosts, but for bridges we didn't perceive it as optimized. The option that we considered was, of course, to have a straight central part and then to curve only the ends at each side. This was possible, but if we wanted to avoid splicing of the main beam, it had to curve only for a length below 35 meters, and we wanted, as I mentioned, to go above 40 meters, so 45, 50, 55 meters. There is also some limitation in the curving of these tall beams. So at the end, the geometry was very similar to the one of the bottom flange of the existing solution. So we didn't consider it as most optimized. And we take the solutions to have three segments which are welded together by full penetration splice. And the location of this splice gives the angle, and it should be optimized in function of the clearance height. On this slide, we show the main parameters of the system, where we see that there is a slender central part and a most, would say, massive frame corner, which gives a lot of stiffness and resistance. And the slenderness of the foundation is more or less the same as the one of the corner taken in a vertical direction. The length of the leg, so this inclined part, is about 1/10, 1/8 of the total length of the bridge on each side. This is the cross section where we would have a rolled girder, high strength, reinforced eventually with a reinforcing plate welded below the bottom flange. We have a prefabricated concrete slab, and then we have an in situ concrete poured on top of it. We have made a parametric study with different cross sections, so national, local, and highway. So this is the road which has to pass above the existing highway. And with these three solutions, we have made a study with 40, 45, 50, 55, and 60 meters really to optimize the steel consumption and optimize the solution, always compliant with European design. So the results have shown that the slenderness is comparable to the one of the existing system for when it comes to the central part, and it is a bit more slender at the supports, thanks to this fact to have high strength steel and to have a massive concrete slab in correspondence of the hogging moment region. So typically the slenderness is L/17, L/20 at the supports, and L/30, L/35 in the span. The steel consumption is lower than the one of conventional S355 solutions, mainly thanks to the shape and to the fact that higher steel strength are used, such as S460 or higher. Of course, there is more effort which is put in this corner frame, which is quite massive, and where a considerable amount of concrete is poured. In this case, the economic impact is relative, and the static impact is also modest due to the fact that this weight is close to the supports. The economical comparison between the two solutions showed benefits at about 140 euro per square meter, which is considerable. It is about 50% of the prefabricated part between the existing solution and the new solution which is proposed. We come now to the last part of the presentation, which is the design tool that was developed to design such frame bridges. The new software advanced bridge that was developed by ArcelorMittal with the partner Grytec, which is available on our website free of charges, and we are very happy to receive comments from your side. It was implemented also the possibility to design such frames, so with a concrete deck which is of different inertia and with different layers. The software has already implemented the different bridge loads, so like LM1, permanent loads, and gives you the bending moment for different charges, and permits to have detailed design for the steelwork as well as for the shear studs. So this is how we imagine a new optimized overpass. I have finished my presentation and I thank you for your attention. I am open to your remarks or questions.